Welcome to qnawire.
We know that for the circular orbit of the space vehicle about the moon, the force acting on the space vehicle F is equal to mv squared over r, where little m is the mass of the space vehicle, v is its speed of its orbit, and r is the radius of its orbit about the moon. But the law of gravitation tells us that this is equal to g times the mass of the moon times the mass of the space vehicle divided by the square of the distance between them, the square of the orbit, r squared. So if we equate these two, we can see that we can formulate an expression for v squared, where v is the speed of the orbit, and v squared is equal to gm over r. So we can use this equation and we can find the circular orbit A. So the initial circular orbit squared is equal to, and we'll just substitute our values in here, so that's 66.73 times 10 to the minus 12 meter cubed kg per square second. So we'll just suppress the units now, times 73.49 times 10 to the 21, and that's kg. So again, that's SI units. That's the mass of the moon over the radius of the orbit. For A is 2,200 times 10 to the 3 meters. And hence, if we take the square root of that, we get the circular speed, or the speed of the circular orbit of the satellite at orbit A is 1,493 meters per second. Now we can do the same for the circular orbit B. So VB squared is equal to, again, we'll substitute our values in here, 66.73 times 10 to the minus 12 in SI units, times the mass of the moon, which is 73.49 times 10 to the 21 kg, all over the radius of the orbit of B is 2080 times 10 to the 3 meters. And hence we get the circular, or the speed of the circular orbit of the satellite in orbit B is equal to 1,535.5 meters per second. So now we have the speed of both orbits. So the first thing we want to do in part A is find the transfer velocity at orbit A. So the transfer velocity, we'll call it TR, is equal to the speed of the circular orbit, VA circular, plus delta VA. Delta VA is the speed difference, or the speed change, when transferring orbits. So this is 1,493, which we calculated above, minus the given rate, 26.3, and that's meters per second. Hence we get VATR to be 1,466.7 meters per second. And now we'll apply the conservation of angular momentum. So the conservation of angular momentum requires that RA times m VA at the velocity t VATR must equal to RB m times VB TR. VB TR is what we wish to solve for. So if we rearrange this equation, we can see that the transfer velocity at point B is equal to 2,200 kilometers, which is VA over VB, or RA over RB, 2,200 over 2,080 kilometers times VATR, which we calculated to be 1,466.7 meters per second. Hence we get the velocity of the satellite at point as it approaches point B on its elliptical path to be 1,551 meters per second. Now we wish to calculate delta VB, where delta VB is the amount by which its speed should be reduced as it approaches point B to put it into the smaller orbit. We know that the circular speed of B, VB, is equal to its transfer velocity in its elliptical orbit, VB TR, plus delta VB, and we wish to solve for delta VB. So if we rearrange this equation and make delta VB the subject of the formula, we get delta VB is equal to 1,535.5 minus 1,551.3 meters per second, and hence we get delta VB to be minus 15.8 meters per second.